So in this video, we're going to talk about a reaction energy diagram and some more. What are some of the characteristics? How do we differentiate endothermic versus exothermic, and some of the factors that contribute to a reaction being exothermic or endothermic. Now, usually on the reaction energy diagram, we have a y-axis and an x-axis, and on the x-axis, we usually have the reaction progress. On the y-axis, we have the energy. Now, a typical graph that you will actually see is something that looks like this. Right? Now, we're going to label this diagram and talk about some of the characteristics. So, furthest to the left of the diagram at this point is actually where we have our reactants. Now, furthest to the right at the end is where we have our products. Now, as you can see, furthest to the left, we have kind of two hills, or what we call it transition states, that the reaction is proceeding towards, right? So the reactants are going towards product. And I can see that we have two hills, or what I want to call them hills. The higher one is actually what we actually call the rate limiting step. Right? It takes the most energy to overcome. So the higher hill essentially is actually what we call the rate limiting step. Now, as with all reactions, in the middle is where we have our intermediates. Now, in chemistry, you usually see that at the top of these hills, we usually denote it by something like that. And at the direct top of this hill, where those kind of number sign looking things are, is what we actually call the transition states. So these are what we actually call the transition states. Now, we know that the free energy equation, or Gibbs free energy equation, says that delta G is equal to delta H minus T delta S. Now, what I want you to take away is that if the delta G is negative, we say that the reaction is exothermic, or in other words, spontaneous. If the delta G is positive, then it's the opposite. So we say this is endothermic in chemistry. Right? In biology, the biology folks might say, well, it's endergonic or exergonic. Here we're using it or endothermic and exothermic language. Or in other words, if a delta G is positive, the reaction is non-spontaneous. Now, let's talk about some scenarios that may lead to a reaction being non-spontaneous or spontaneous. Now, remember again, if our delta G is negative, we say the reaction is exothermic. It's spontaneous. If the delta G is positive, we'll say the reaction is endothermic and non-spontaneous. Now, if you look at the energy diagram that I've drawn, what I want you to take away is that look at the energy. The reactants had a higher energy than the products themselves. And so we call this a downhill process, or in other words, let me kind of draw a line to demonstrate. The reactants had a higher energy than the products, so we're looking at a downhill process. And so this is what we would call a exothermic diagram, right? The reactants are at a higher energy than the products. Now, the opposite is true. If you look at this diagram from right to left, instead of looking at it from left to right, and replacing the products with the reactants, looking at the diagram from right to left, now it will be going uphill, right? So if I replace this end, with the idea of reactants and then essentially going to products, then this is what we call an uphill process. And so that diagram would be considered an endothermic reaction, right? So for simplicity, all I'm saying is that if I give you a reaction diagram where I have my energy E on the y-axis and I have the reaction progress on the x-axis, and let's say this is a simple reaction, so there are really no intermediates. For an endothermic reaction, it would be an uphill process. So the reactants essentially are going to be lower than the products. And so the graph may look like this, where these are my products and these are my reactants. The same thing is true for the opposite is true for an endothermic reaction. And so we say this would actually be endothermic. And let me erase this. Right? But essentially, the same thing the opposite would be true for an exothermic reaction, which we actually drew above. Right? But again, like we said before, the reactants would be at a higher energy than the products. And so this is a downhill process. Right? So here's our reactants. And there is our products. Right? Now again, like we said before, at the top of this hill we have our transition state, and so this would be an exothermic reaction. Now let's go back to the idea of our formula, delta G is equal to delta H minus T delta S. Now for a reaction to be exothermic, what we're saying is that delta H must be negative, and our delta S, which represents entropy, must be positive. In other words, let's look at the formula to make sense of this. If we have delta G being equal to delta H minus T delta S, where T is our temperature in this case, remember we said that if delta G is negative, that constitutes a spontaneous reaction, or in other words, an exothermic reaction. Now, in order for this delta G to be negative, that means that my delta S has to be really positive. In other words, really positive. This will essentially give me a really negative number, right? Because remember, I have a negative that's being distributed to both the temperature and the delta S. So if the change in entropy, in other words, or delta S is positive, then this number becomes really negative. So I'm substituting maybe a positive number from a really huge negative number, and so essentially my delta G would be negative. So the opposite is actually true, right? So if we're looking at an endothermic reaction, we actually want delta H to be positive, whereas delta S, or the entropy, to be negative, right? In other words, if we look at the formula, what we're saying is that delta H is really positive, so that's a really big number, minus, well, delta S being negative is actually good, because now we're distributing a negative times a positive number in the temperature, but we also distributing a negative times a negative number. And so essentially what we're really getting is a positive number. So delta H becomes positive, whereas our distribution allows T delta S essentially to become uh, less negative. And so essentially we would essentially get a positive number, and so that constitutes an endothermic reaction. Right? We already spoke about the rate limiting step. Now the last thing I wanted to mention is that, say we have a curve and we have some sort of, let's say these are our products B and we have our reactants A, and by this graph you should be able to tell there's a free energy and there's a reaction progress. By this graph you should be able to tell that we're looking at an exothermic reaction. Now if I theoretically ask you that if the products of B were lowered, right? So I'm sorry, if the free energy of B was lowered, right? So we're talking about the products. If we actually lower the free energy, so in other words, decrease delta G, what would happen as a result? What you would find happen as a result is that the equilibrium constant, right? So the equilibrium constant in this case, we know our equilibrium constant is equal to the products over the reactants. So in this case, I'm going to say the concentration of B over the concentration of A. It would actually increase. Think about it. If the free energy of the products are being lowered, what we're really saying is that we're making the reaction more exothermic. In other words, the deeper the slope of, in other words, this point of the curve, the deeper the slope of this point of the curve, the more exothermic the reaction is. Now, conversely to that, and the opposite should be true, right? If you increase, or in other words, if you increase the free energy of the products, you should expect the equilibrium constant to decrease in that regard. Now, what about the transition state? The transition state is actually really important. What happens if you actually lowered the transition state? What do you think happened to the reaction? This is a very key point. The transition state does not affect the equilibrium constant. So let's say that again. The transition state does not affect the equilibrium constant. It is only the energy of the reactants or products that alters the equilibrium constant. So the transition state has nothing to do with the equilibrium constant. Rather, the transition state actually is equivocated to the overall rate of the reaction. So the rate of the reaction and equilibrium constants are two different things. Now, if you lower the transition state, the overall rate of the reaction would increase. In other words, the slope would be actually lower, right? So what I'm saying is that instead of looking at this graph at the top, we may see something like that, where the slope is a little bit lower. And so the reaction will easily progress to the products. Now, the opposite should be true. If you increase the transition state, you should expect the overall rate of the reaction to decrease. So the transition state, in this case, if we lower the transition state, the overall rate of the reaction should increase. Right? So the rate of the reaction should increase. And these are the basics that you guys must know for an energy reaction diagram.